So the next speaker of this session is Fabian Reimers from Munich, and the title of his talk is Symmetric Polynomial Vector Invariants of Symmetric Groups in Characteristic Zero.
Yes, thank you very much, and thanks to the organizers for assembling us here. So I want to talk about some joint work I did with München about vector invariants of permutation groups in characteristic zero. So it's all very classical stuff, as we will see in a moment. So let's start by fixing the notation, the setup. We will have a finite group G, and K is the field. And we look at a finite dimensional representation of this group. And then, of course, we have the polynomial ring in n variables. Could think of it as the coordinate ring, the ring of coordinate functions on V. And inside here, we have the classical object, the invariant ring that we are interested in. And of course, in a moment, this will be more specific. We will have permutation groups, not just any finite groups, and not just any field, because as the title says, what we did was in characteristic zero. But for the moment, let's just look at this general setup. Let me define the so-called beta number or Noether number, which is the smallest integer d, such that the invariant ring is generated as a K algebra by homogeneous invariants of degree at most d. So in our previous talk by Vesely and Drensky, we had a nice overview about results of classical invariant theory. And of course, you know, for finite groups, the invariant ring is always finitely generated. So this number really is an integer. And we could also think of it as the highest degree that appears in a minimal homogeneous set of generators of the algebra. So I want to talk about permutation groups. So a permutation representation, of course, is just a representation where the group acts as a subgroup of the permutation matrices. So the fixed basis of the vector space is being permuted by our group. Maybe I should say the fixed basis, because of course we already had the basis fixed up here, right, with the coordinate functions. As you probably know, there's the celebrated theorem by Göbel about invariance of permutation groups. Let me start with this theorem. If we have a permutation representation of degree n of our finite group G, then there is a degree bound known for the invariant ring. The invariant ring is generated by invariants of degree at most n choose 2. Let's say n is bigger than 3, so that this case is, you can forget this case. If n is at least 3, then the degree bound is easy to remember. It is the invariant ring is generated by invariants of degree at most n choose 2. And this was proven in a very general situation by Göbel in the 90s. So K is just any field, and it was known before in characteristic zero. And Göbel's theorem is, of course, more precise than just this degree bound. It tells us that the invariant ring is generated by certain orbit sums. Well, this is always true for permutation groups, but we don't orbit sums of monomials, but we don't have to take all monomials. We only have to take what he called special monomials, which are monomials that have no gap in the exponent sequence. So something like x1, x2 cube would not be a special monomial because there's nothing squared in the exponent sequence. So yeah, this is special monomials, and together with the monomial x1 times up to xn. So this is the famous theorem by Göbel, and what Müfit and I did is we tried to look at vector invariants in this case of permutation groups. So let me quickly remind or define what we mean by vector invariants. We always mean that we simply look at the direct sum of this representation with itself. So for some integer, non-negative integer m, we have this representation, the direct sum of V with itself, and then of course G acts diagonally. So now the invariant, the coordinate ring, the polynomial ring where we also have the G action would be something like this, and of course we have to use double indices here or whatever. So the variables are now denoted by xij, where I is the ith coordinate function on the jth copy, right? We have m copies, and on each we have n coordinate functions, just to keep the notation in mind. So, and we will be looking mainly at permutation representations, where, of course, the action now can be written down like this. The action here is diagonally on the jth copy. Everything stays inside the jth copy, and yeah, the variables are permuted as they were before. So when you look at vector invariants, typically the invariant rings get more complicated and the degrees of generators tend to grow. And yeah, let me present our result. So for a permutation representation of this finite group G in characteristic 0 is here, and this is the degree n of the representation. We have a similar bound to Goebbels' bound. We have that the invariant ring of the vector invariance is generated, this is here in this better notation, right, is generated by invariance of degree at most n choose 2 plus 1 is what we can yeah, do here. So maybe at first a few comments. First, let me jump back one more time to Goebbels' theorem for maybe a few people in the audience who might not have seen this before. We have this Goebbels theorem where we looked at permutation representations and we had this bound n choose 2. And now what we did is we looked at vector invariance copies of this representation. Okay, so first I want to make a few remarks about the modular case, which obviously is missing here from our theorem. So modular case, by this in invariant theory of finite groups, we always mean we now have a field of positive characteristic, and this characteristic divides the group order. Then, as most of you probably know, there's this famous lower bound by Richman. If we have any finite group in this modular case, and we look at vector invariance, we look at copies here of the representation V, then there can be no degree bound that only depends on the group order or the dimension n. This degree will go to infinity if m goes to infinity. Oh, I just see, I should add, of course, here is meant we have a faithful representation, right? It's not the trivial representation, faithful G module. Then it was shown in the 90s by Richman that the degrees of vector invariance can be bounded from below by something, by a constant times n. And for the case that we were interested in, permutation representations, this was also also looked at in this modular case. So this here is meant like the modular, this assumption is here for all my bullet points. So for any permutation group, the lower bound was improved or looked at more specifically in a paper by Kemper in 1998, and where he could show that for a permutation group, the better number in this modular case is bounded from below by m times p minus 1. And even more specifically for the symmetric group, and for the symmetric group where n really is a power of this characteristic p. This was looked at by Peter Fleischmann in another paper in 1998, where he explicitly could calculate the degree, the better number of this invariant ring, always here vector invariance, right? So it seems like this business of looking at vector invariance and degree bounds that arise in this situation was popular in the 90s, and nevertheless we looked at it now too, and we could get the result that is still here displayed on the page at the top about vector invariance of permutation groups in characteristic 0. So basically, the rest of my talk I will talk about the proof of this theorem, because it's not a long paper. It's something that we can really see in this 20 or 30 minutes talk. So let me talk about the proof of this theorem. And what's the technique here? There are two main ingredients that are used: polarizations and the Hilbert ideal. So very, very classical stuff. A quick reminder what polarization is in invariant theory. And here again, we could think about any arbitrary group. And later I will specify, or we will go back to our case of a permutation group. So we look at the following K-algebra homomorphism coming from the coordinate ring of V. And remember, here we had the variables x1 up to xn. And then here we had the variables with a double index xij. And then we add additional indeterminates, t1 up to tm. And we replace xi by this sum over xij, tj, sum over j. And we look at this K-algebra homomorphism, and then simply what we do is, if we have a polynomial, we plug it into this map phi, and then we recover the multi-homogeneous part, if you want. We recover the part that belongs to this K is a multi-index, and we recover the part that belongs to this monomials in the new variables tj. And so what we will have here is a polynomial defined on the vector space Vm, and this is typically all these, which are denoted by pol k, all these are called the polarizations of F, or probably all the non-zero coefficients that appear here are called the polarizations of F. And just if someone hasn't seen this before, a quick example that you can look at. And so if we have this polynomial here, and we want to polarize in a second set of variables, m equals 2, then we would replace the x1 here by this sum and multiply everything out. And the tj's are basically just here to recover the multi-homogeneous part of a certain degree. And what we have here will be the polarizations, these coefficients. So a few observations about this. Why does this appear in invariant theory? Okay, first of all, let me just notice for later, this map with a fixed multi-index k here is from kv to kvm, and it's a k-linear map. Then this K-algebra homomorphism here, it commutes with the G action. By this we mean we let G act trivially here, and we have a G action here and here, and then phi commutes with the G action. So it's the equivariant map is another way to say it, and this is the argument why this is important, or why this naturally appears in invariant theory, because now we know invariance will be mapped to invariance for the vector invariant case. So another thing we need is the Hilbert ideal, and this is of course the ideal in KV generated by all homogeneous invariants of positive degree. And similarly, we now have this in our another coordinate ring with a vector invariance. And I need some ad hoc notation because this will appear now later on. So I is the Hilbert ideal, and I index m is the Hilbert ideal here. So another observation about polarization, maybe not so frequently used as like this observation, but another observation is that if we take something from the Hilbert ideal and we look at it as a polarization with always a fixed multi-index here, then this will be in the Hilbert ideal here. So why is this the case? Short observation, short proof. If we take homogeneous invariant of positive degree, multiply it by any polynomial, and then we plug it into our map phi, our K-algebra homomorphism, then we want to collect again later what is the coefficients of something like this here for a multi-index K, and this coefficients will be a sum of products of the corresponding coefficients for G and H. And now if G is an invariant of positive degree, then this will be invariance. And here is some polynomial. So overall, this coefficient here, this part here, will be in the Hilbert ideal for the vector invariant case. So if we take a homogeneous invariant of positive degree times a polynomial, then the polarization will be in the Hilbert ideal for the vector invariance. And since the polarization map is linear, this is enough to show this result, this lemma here. Okay, now we want to specify for permutation groups. So we start with Sn, we start with a symmetric group Sn, and its standard representation on Kn, k to the n. The Hilbert ideal, of course, is generated by the invariance, by the elementary symmetric polynomials, but we could also use this set of generators here. We could have the first elementary symmetric polynomial, and here we have the sum over all all monomials of degree 2 minus x1 times this. So we subtract all all monomials of degree 2 where x1 appears. And it turns out that this here is then also a basis for the Hilbert ideal. And it's not any basis, it's the reduced Gröbner basis of I for this Lex order, for the Lex order with where x1 is larger than x2 and so on. Because basically what we did is we looked at the elementary symmetric polynomials or the full symmetric polynomials, and we subtracted exactly in the way that we would do if we want to compute the Gröbner basis with respect to this monomial ordering. So this here now is a basis for the Hilbert ideal for the group Sn and the standard representation. So the lead term ideal of the Hilbert ideal for Sn is particularly easy, just has x1 coming from here, x2 squared coming from here, and so on. So the lead term ideal of the Hilbert ideal for Sn standard representation is really easy. And this is something that makes it easy for us to work with this. So we want to talk about permutation groups. Notice, of course, any permutation group is a subgroup of Sn. So the Hilbert ideal, now the notation, I'm sorry for the switches, now I is the Hilbert ideal for any permutation group, not anymore for this Sn, but it contains, of course, everything that we had for Sn. So it contains these things, these generators for Sn we had before. So the lead ideal of the Hilbert ideal for any permutation groups contains these especially easy monomials. And especially we see it contains every monomial of degree n choose 2 plus 1, because whenever I have a monomial, if it contains x1, then it is contained in this lead ideal. If it contains x2 squared and so on. So only of degree n choose 2, there might be some monomials like these who are or are not in the lead ideal that we are considering right now. But anyway, we have every monomial of degree n choose 2. And we want to go to vector invariance. So let's fix a lexicographical order on the corresponding coordinate ring for the vector invariance. We just say that the first variable should be always larger. So remember, this is the first coordinate function on the second copy of our vector space and so on, right? So this is one way to fix a lexicographical order here on KVM. And then it's not surprising, but it needs to be checked that if we want to apply now polarizations, and we have two monomials in our original polynomial ring, two monomials of degree d, one is lexicographically smaller than the other, and we look at a certain polarization, and we look at the kth polarization, then the result doesn't have to be a monomial, of course, but the leading monomial of the first one is smaller than the leading monomial of the second one. So if we use this correct Lex order, if you will, then the ordering of the monomials is transported via the polarization. So here I wrote down, we take, of course, a multi-index k, which has the same degree d. Otherwise, this polarization here would be 0, of course. And we use characteristic 0 because otherwise it's simply not true, because polarization could just be 0 then, right? The polarization of the larger monomial could be 0 if it's not characteristic 0. Okay, so this is, I would say, not surprising. This is what I called here lemma 1, but still it needs to be checked. Maybe, maybe we don't have to, maybe we don't want to go through it. Anyway, what we do is we just take a monomial and look at what happens if we plug it into this K-algebra homomorphism phi that was the root for polarization map, and then we check what would be the leading monomial of the kth polarization of the kth coefficient that appears here, and then you can check, okay, if I use this Lex order here, then the leading monomial should contain x11 as much as possible. So you go through how much of how many times can this contain, or must this contain the variable x11, and of course at most a1 times here, but also at most k1 times, because we look at the polarization with multi-index k here. So if you carefully go through this, then you get this result, which is probably not surprising, but needs to be checked with the computation, that the monomial ordering, if we use this monomial ordering, then we get the same ordering here for the leading monomials of something polarized. Okay, so what do we get from this? We get from this that we can take anything in the lead ideal of the normal invariant ring, the leading ideal of the leading ideal of the Hilbert ideal of just one copy. We take any monomial here, we can polarize it and look at its leading monomial, and we get again something in the leading ideal of the Hilbert ideal, now of course for several copies. Okay, so let me say this again. We take any monomial in the leading ideal of the Hilbert ideal, we polarize it for some fixed k, or for all k, of course, is what we're interested in, for some fixed multi-index k, and we look at the leading term that appears here, and this will be now in the leading ideal of the Hilbert ideal of vector invariance. Again, of course, polarization really is only simple to analyze if we have characteristic 0, right? Because the coefficients otherwise might disappear, and then the stuff about which monomial is higher might be true or might not be true. Okay, so why is this now true? I take here something in the leading ideal of the Hilbert ideal. So let's just assume it is the leading monomial Lm, the leading monomial of something in the Hilbert ideal. Then this thing in the Hilbert ideal can be written down as a sum of its terms, and we have its leading term, and we have all the smaller terms. And then polarization for the kth fixed coefficient is a linear map. So of course it will look like this. And we said earlier, if we take something in the Hilbert ideal and we polarize it, then this will again be in the Hilbert ideal of many copies. And now by our previous lemma 1, we know that every monomial that is smaller for m, after polarizing, the lead term will also be smaller than the lead term of the polarization of n. So we really know that the lead term of f, the lead term of the polarization of f will come from this part, right? And this is what we want. We want to observe that we make ourselves, we make life for ourselves easier by just polarizing the lead term, and then we will get the lead term of the whole polynomial f. Okay, so now we can, come to the last part, to the proof of the theorem from Müffet and me. So let me quickly recall, we had characteristic 0, and we had a permutation group. In fact, I think I should maybe go back for 1 second. So we had characteristic 0, and we had a permutation representation of a finite group, and we look at vector invariance, and then we have this degree bound of n choose 2 plus 1, not depending on the number of copies here. And yeah, we talked about how this is not possible in the modular case, but now we assume characteristic 0 in the permutation group. So we said, because we have a permutation group and because the Hilbert ideal for Sn was so easy, we know that the lead ideal of the Hilbert ideal contains these monomials, and they are very easy to polarize. This is just one variable to some power, which is, easy to plug in our map phi, the K-algebra homomorphism that defined the polarization. We use the sum over now the different sets of variables, each with a new indeterminate tj, and we just multiply this out, multinomial theorem, whatever it is called, and you see that for any multi-index which has the same degree as this exponent I here, otherwise the polarization would be 0. The polarization corresponding to this multi-index of xi is this monomial times some factor, but we made life easy for us and assumed characteristic is 0, so this factor will be non-zero. So what was the argument here? We know these monomials are in the lead ideal of a permutation group by observing, okay, polarizing stuff and looking again at the lead terms, polarizing stuff here, it even is again a monomial. These monomials are now in the lead term ideal of the Hilbert ideal of several copies. And now this was true for every k that we can look at here. So maybe to make it a bit more specific. So for the first variable I equals 1, we had x1 here, and now we get x1 first copy, x1 mth copy in the lead term ideal. For the second variable, we had x2 squared here, and now we get x2 jth copy squared, but also these are in the lead term ideal, and so on and so on. So basically, we see that all monomials of degree n choose 2 plus 1 are now in the lead term ideal of the Hilbert ideal of several copies. And so from this, we can observe, okay, this ideal must be generated by homogeneous invariants of degree at most n choose 2 plus 1. And again, we also had this in our previous talk, some results about classical invariant theory. We are in the non-modular case now, and our line of argument is we want to show the invariant ring is generated by homogeneous invariants of degree at most this. But we can use the Reynolds operator to get generators of the Hilbert ideal and to get from generators of the Hilbert ideal corresponding generators of the invariant ring. So this is the idea of our proof. So apart from a few computations or observations, I think it is possible to follow it in a short time. It's not a long proof, and that's already the end of my talk. Thank you very much, and thanks.
Thank you very much for your talk. Are there any questions or remarks?
Well, I have one question. Fabian, can this method be applied to some particular permutation group? For example, for the alternating group, do you know explicit bound B in case of alternating group?
No, we don't. No, I don't know, and I think I think the answer would be no, or at least I would say no, because it turns out that you don't get all the generators of the Hilbert ideal just by polarizing. As the same is true for the invariant ring, that simply polarizing usually doesn't give all the invariants needed to generate the invariant ring for vector invariants. Of course, there's Weyer's polarization theorem that if you have already n copies, you can go to more than n copies, but to go from 1 copy to 2 copies, usually only using polarization is not enough. So and we tried to look at the example of AN, or maybe just A3, A4 of A5, and we couldn't get any further because we couldn't get all the monomials that we want to make another statement just by looking at the polarizations.
Okay, and then I have a very naive question. And so what is explicit bound for Sn here, this one?
Well, this is really just permutation representation. So for Sn, it will just be the standard representation, right? So all elementary symmetric polynomials, so n.
No, when we have several copies.
Isn't it also?
Doesn't change the degree, so it doesn't matter.
Yeah.
Still n.
It's still n. It's the
Polarization. If you take polarize some polynomial, it doesn't change the degree. So for one copy, if it is something, then for several copies, it's the same.
This is the theorem of Schläfli, which was mentioned in the previous talk in the 19th century.
It's also.
Isn't it that the degree remains the same?
For Sn, yes, it's also in the book of Weil, right, where he looked at multisymmetric polynomials and showed that the polarization.
For Sn, the polarization is generated.
Yeah.
Okay, and then did you try to look at some maybe very small groups in case of you're bound to try to verify is it explicit or not? Maybe for some very small groups, if group is small, then probably bound is very high, and maybe your bound will be explicit.
Yeah, no, to be honest, we didn't do much further in that direction. No.
Okay. So I think there is room.
Yeah.
For possible research.
We check maybe, yeah.
So, do you know of any groups where Goebbels bound is the best possible bound?
Yes, that's true for the alternating group, right? Because their Goebbels bound is n choose 2, and you have the discriminant, or you could, for the alternating group, you could use the orbit sum of x1, x2 squared. Yeah.
Yes, okay, that explains Artem's question, doesn't it? Yes,
for,
I see.
For the alternating group, Goebbels bound is sharp, yeah.
Mm-hmm. Okay.
So do you really need this +1?
Yeah, that's a good question. I'm not sure, to be honest. This just came naturally from this argument of proof, but yeah, could be that you can get rid of the +1 here, yeah, and make it really analog to Goebbels' theorem, yeah.
So it seems that there are no more. Oh, maybe there's a question in the chat or comment.
Yeah, there's an interesting comment in the chat, but no more questions.
I cannot read, so how can I read the chat?
It's on the bottom right, the second button on the bottom right for me, it is.
Oh, yes.
And it's thanks for the comment by Benjamin that in characteristic 0 Goebbels bound was proven much earlier, actually. Yeah, I wasn't aware of that. Yeah.
I have just one follow-up question. Did this formula of your bound, did this appear on the proof of Professor Tao on the prime number theorem?
I have no idea, to be honest.
Okay. It seems to me that this one is a bit similar to that one used by Professor Terence Tao. Anyway, thank you.
That's an interesting remark. I might look into that, but I don't know. Yeah.
So it seems there are no more questions. So thank you very much again.
Yes, thank you all again.
And we can continue in 2 minutes.